Why is the universe not 13.8 billion light years wide? Could a black hole possibly consume the entire universe? Where did all the metals come from? In Q&A Plus, what's the best part of my job here? All this and more in this question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down, I'll gather them up, and I will answer them here. All right, let's get into the questions. Anon Liddy. Explain it to me like I'm 5. Why the observable universe is 93 billion light years across, yet it's actually bigger than that. How wide is it actually? So here's the explain it to you like you're 5 version. And this is, I'm going to go back to my example of the Fogiverse. So imagine you're standing in fog and you can see about 30 meters away. Right up close to you, you can see your hands. There doesn't seem to be any fog in between your hands. Cars nearby, you can see they're slightly obscured by fog. And then the very limits of the fog is, say, 30 meters away, very thick fog. And you say, well, like, how big is the world? Well, the world that you can perceive is 30 meters. And yet you hear sounds that sound like they're coming from very far away. So the world has to be bigger than what you can observe in the fog. That's it. There's the explain it to you like you're 5. So when we look out into space, we're looking back in time. So when we look at the sun, we're seeing the sun as it looked 8 minutes ago. When we look at Andromeda, we're seeing as it looked 2.5 million years ago. When we look at the cosmic microwave background radiation, we're seeing it as it looked 13.8 billion years ago. That the photons that left some place in the universe have been traveling for 13.8 billion years to finally reach your eyes. That is the very limit, because that is the first light that was released into the universe. We are not seeing, when we sort of imagine this sphere of the observable universe around us, you don't want to just think of it like space. You want to think about it in terms of, I am looking back in time. And it's weird because like your brain can handle this nearby, and then after a while this starts to lose meaning, right? If I tell you that you're not seeing the sun as it looks right now, you're seeing the sun as it looks 8.5 minutes ago, you're like, okay, I got that, right? No problem, right? So if there's a flare on the sun right now, I have to wait 8 minutes before I can perceive that flare. Great. So imagine, right, that all the stars in the entire universe have a flare at exactly the same moment. They all flare. For some reason, some kind of magic reason, they all flare at the precise same time. What will you see? You'll see the sun flare, and then 4.5 years later, you'll see a flare on Proxima Centauri, and then 10 years later, you'll see a flare on, I don't know, Bernard star, and then 2.5 million years, you'll start to see flares in the stars in Andromeda. You're seeing this kind of propagation of these flares. And so us seeing light in the universe back to the very beginning of the universe, this 13.8 billion years, it's the same thing. We are seeing light that has had time to travel to us. We cannot see farther than 13.8 billion years ago, because that's how the longest light can have been traveling in the universe. But that, when we look at this region of space, and as you said, it's 93 billion light years across. That's sort of the size of the entire observable universe. Those places that we see right at the very edge of what we can see, we're not seeing them as they look today. We're seeing them as they looked 13.8 billion years ago. And so they do look different today. Like if you could magically transport yourself to that place at the very limit of what you can see, you would see the modern version of that, not this release of radiation from the very beginning of the universe, but there would be a galaxy there. And you would be able to see the planets and the stars and so on in that galaxy. And then, but when you were at that point, you would now see a new observable universe around you that is 93 billion light years across. And then if you move to the very edge of that observable universe you could see, now you'd be in the middle of a new one. And so then the big question is, how far could you keep doing that? Could you keep jumping to the edge of your observable universe and then look around in this new observable universe and then jump to the edge of the next one, the next one, the next one? That either it's infinite, you could just keep jumping forever, that there is no end to the universe, that it just goes on forever. And the other possibility is that it's finite, that if you kept doing that jump, you would return to your starting point. In the same way that with the fog, that we talked about at the beginning of this conversation. That if you jump to the very edge of the fog that you can see, you would see a new fogiverse around you, and you would jump to the edge of the new fogiverse. And let's imagine the entire planet was covered by fog. That eventually you would return to your starting point. You'd be like, wait a minute, this fogiverse feels very familiar to me. I'm back home. And yet you were just traveling in one direction. So I hope that helps. I understand that it's like trying to hold all these separate thoughts in your brain simultaneously is tricky, but just give it time. You'll get there. Wendell Broadwell, could it be that in the far distant future, the whole universe could be absorbed into one colossal black hole? Would Hawking radiation prevent that from happening? No, but it's a very interesting question to kind of think about what the future of the universe looks like. So right now we live in this time where we can perceive other galaxies around us, that we can look back to the cosmic microwave background radiation, that this is something that will only be possible for about the first 100 billion years in the history of the universe. When we look at all those other galaxies, we can see that the vast majority of them, apart from like 2, are speeding away from us. And they're just getting farther and farther. And in fact, thanks to dark energy, the speed that they are moving away from us is increasing. And so they will eventually be so far away from us that they will fall over the cosmological horizon, that we will no longer see them sort of speeding away from us, that essentially they will fade away into the sort of background of the universe, that even with giant radio telescopes, we won't be able to detect their red-shifted information, that some future civilization 100 trillion years from now won't see any evidence that there were ever other galaxies in the universe beyond the one that they're within. So this idea of all of the universe coming together into one big black hole is impossible because all of these galaxies are being carried away from each other. So let's just focus in on the local group, which is our galaxy, Andromeda, M33, the Triangulum galaxy, as well as the several hundred dwarf galaxies that are orbiting around in this big constellation around our galaxy. They will interact with each other, and some percentage of them will merge. Some other percentage of them will be kicked out in three-body interactions and thrown away from outside of the gravity well of this combined thing. So eventually there will be this line where some of the stuff is bound by the mutual gravity and some of the stuff has been kicked out. And you'll end up with this galaxy, some future giant elliptical galaxy version of the local group. And you can see examples of what giant elliptical galaxies look like. You can see M87. M87 contains a supermassive black hole, which was one of the ones that was captured by the Event Horizon telescope. So it's a very big galaxy with a very massive supermassive black hole, one of the biggest that we can see in the sky. That's kind of what we will look like. And so, yeah, we will get a much more massive supermassive black hole at the heart when the one at the heart of Andromeda meets the one, the Milky Way, and the one, actually, it's thought that maybe M33 doesn't have a supermassive black hole, but there's going to be some other black holes. They'll all come together and merge into this single black hole. There are also about 100 million stellar mass black holes located in the Milky Way, probably many times that number in Andromeda, probably the same number over in M33, plus all the black holes that are in all of these dwarf galaxies. So they will all join this community. Some will fall and sink down and be absorbed into the big black hole at the center of this new galaxy. Others will be kicked out through three-body interactions. And then, over very long, deep time, one by one, the stars will be kicked out of this galaxy. That you will have two stars come together. They'll meet a third star. There'll be a three-body interaction. Stars will be kicked into escape trajectories and they will leave this galaxy, and then they will be part of this acceleration of space and they will fall over the cosmic horizon one by one. And eventually, you'll just be left with the supermassive black hole at the heart of the giant elliptical galaxy that was once all of these separate galaxies and all of these separate dwarf galaxies. And there will be no more material to fall into that black hole. There will be the cosmic microwave background radiation will be incredibly cold, and then that supermassive black hole will start to evaporate because of Hawking radiation. And after about 10 to the power of 100 years, a Google years, that supermassive black hole will have evaporated. And this will be the same process that's going to happen for every other galaxy group out there in the cosmos. Some will be much, much bigger. The ones at the ton 618 or the Phoenix cluster, you've got supermassive black holes that will have maybe 10 billion solar masses. In other cases, you're going to have dwarf galaxies, single dwarf galaxies, where maybe there's only a 10 million supermassive black hole. But that process is going to happen in each one of them. And so no, everything isn't going to combine into one black hole, but every local group is going to combine into their own black hole, kick out all the stars, and then the black holes are going to evaporate. It's time to shout out all the new $5 patrons and above. Disaster Arena, Patrick Thompson, Tim Paget, Help, I'm Stuck on Mars Without Any Oxygen, Robert Schramm, Paul Saxby, Clinton Hunterman, Kevin Davis, Thomas J., and Liam Forkbeard. Join the club at patreon.com/universe today. David Payton, if the universe is only 13.8 billion years old, where did all the heavy metals come from that are under our feet? So 13.8 billion years was enough time for the universe to get up to some shenanigans. So the process of creating heavier elements is called nucleosynthesis. And there have been a bunch of processes since the very beginning of the universe where this works. So the classic, the oldest one, is that at the very beginning of the universe, when the entire universe was in this hot, dense state, the universe was like the core of a star. And hydrogen was fusing into helium for about 13 minutes early on in the universe. And then the universe had cooled down to the point that it was no longer high enough temperature for that nucleosynthesis to work. And that froze out the fractions of hydrogen to helium that we see today, about 75% hydrogen, 25% helium. And then you had stars form. And stars will sort of, as they die, the earliest stars were very big, and then they would die, explode as supernova, and that would seed heavier elements, and they would form heavier elements way up into gold, lead, all kinds of stuff. We also see heavier elements produced by stars, even stars like our sun, as they die. They puff off their outer layers. They are bleeding off oxygen, nitrogen, various chemicals into space that they formed when they were going through the process of nuclear fusion. And the sort of really exciting, kind of interesting discovery was made with the discovery of the kilonova in 2017, where we realized that colliding neutron stars, when they smash into each other, they form heavy elements and spread that out into the universe. That in the kilonova, they saw several times the Earth's mass in gold formed just in this moment, in this collision between two neutron stars. And we actually can now detect the presence of layers of material here on Earth formed by supernova. So there are these layers of iron that are found at the bottoms of the ocean where a supernova went off in our vicinity, exploded, threw iron out into space. That iron made its way to Earth, got through the atmosphere, and collected in this layer around the entire planet. And we actually detect that. So you just have, generation after generation of stars living and dying, seeding the universe with heavier elements. Did you know that you could watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. This week's bonus question: what's the best part of my job here? And I'll put a link down in the show notes. All right, those were all the questions that we had this week. Thank everyone who asked your questions into the YouTube comments, everybody who joined me for the live show. I'm going to talk once again to remind you about the Perseids meteor shower. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bode, Carolyn, Chuck Hawkins, Commander Baylock, Dark Finga, David Giltonen, David Matz, Enthralled Reading and Math for Toddlers, Evan.Pro, James Clark, Jeremy Mattern, Jim Burke, Marcel Smits, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepAnimals.org. Please follow my nephew at VBrick6994, Rinkaidu, Richard Williams, Sean Sargent, Stephen Filer Munley, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klatz, Zelda. Oh my God, we have proof of aliens who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So about a month and a half, 2 months back, I reminded you of some of the really cool things that are happening this summer if you want to go out and look up to the night sky. And the one that is the highlight, on the regular highlight during the summer for the Northern Hemisphere, is the Perseids meteor shower. And this is the one that I try not to miss because I live in the Northern Hemisphere. And that is sort of one of the times when you can lie outside all night with your eyes to the sky and watch meteors. The Perseids aren't the best meteor shower. They don't have the most meteors. You get between 50 and 70. Depends on how much of a moon there is. They peak August 12th, 13th, so the night of August 12th and into the morning of the 13th. And it doesn't really matter where you are, wherever you live, you'll be able to watch the meteor shower. Northern Hemisphere, Southern Hemisphere, doesn't matter. And it doesn't matter where you have to look. You can look just up into the sky and you will see the meteors sort of leading back to the Perseus constellation. But you can see them anywhere in the sky. And this year is special because there is pretty much no moon. And that means that you're going to be able to see the fainter meteors. But you've got to go somewhere with good dark skies. This is one of those events that you can just count on. You can go outside, lay on the grass, on a blanket, on a chair, look up, and you will see meteors. And you will see them dependably, many every hour. And it's a really good time. And often, I used to do this with my kids, fall asleep under the stars. But for the best viewing, you want to get to a place with dark skies. So if you live in a place that has nice dark skies, good news. Just walk outside, lay on the grass, look up. But if you live somewhere with some light pollution, you should try and plan out some dark skies to get to. The tool that I recommend to people is called the Dark Site Finder. And this essentially just puts a light pollution map on top of a Google map. And so then you can look around for the darker skies. And you don't need to go to all the way to the darkest possible skies. You just have to get a few grades darker than where you currently are. And often that means getting, an hour out of town, try to put a mountain in between you and light pollution, things like that. And so plan this out. It's a really good time. Gather together a bunch of your friends, go camping, and enjoy the Perseids meteor shower. All right, we'll see you next time.